Basically, because this solar charge controller will only light up when the battery is connected. And then because we have a different set of menus here from the solar charge controller, we have like the charging menu, we have the floating voltage menu, where if we want to check whether it is working or not, we can check if the battery is charging or not. Because let's say if it's in the morning, because there is sun, and also the photoresistor will detect the radiance and it will switch off the relay, so it won't provide any power to the street lamps. But and that said, it will mean that the power source will be charging the battery. Okay. But if one of them is not working, that's why we went with the parallel configuration. Yes, because if series, then all of it will cut the power. Okay, and then finally, from the solar charge controller, it will charge the battery, and then we will feed the power to this DC load to the street lamp itself. Okay. Now I was in Malaysia. If you can see the global wind atlas, I did some research. Malaysia's average wind speed is around 4.1 meters per second. This turbine needs only 2 meters per second to start, and also it doesn't need high wind speed of 5-10 meters per second to maintain its rotational motion. That's why not only that it's low wind startup speed makes it suitable for urban settings, it also have good resilience in extreme weather conditions because the placement of this gearbox and also the turbine is at the bottom. If you see traditional horizontal axis wind turbine, they spin in the horizontal axis. The gearbox and also the electronics is placed on top of the nacelle, and it will make things okay. Let's say if there is a tornado, usually the HAWT, they will have a yaw system to automatically adjust their positioning. If let's say the speed of the tornado gets above 10 meters per second, it will not be able to sustain the automatic adjustment, and then it will break. That's why we have this vertical axis wind turbine, because we don't need any active adjustment system. We just need it to be to pin the turbine itself, and then we can just place it on top of the gearbox. And also, this turbine is omnidirectional. What I mean by omnidirectional? It can capture wind from all directions. So let's say if wind comes from here, you can capture it. From here, you can capture it. But if horizontal axis wind turbine, like I said, they need the active yaw system adjustment. So if there is wind over there, they need to adjust to the side. And also that adds up the cost, because those are moving components and they will wear down something. This one, we don't use any of them, so it is more cost effective. And finally, we have the simpler blade generating. Why? Because this turbine, we 3D printed it. As we know, 3D print, we print from the z-axis, from the bottom to the top. But for the HAWT, you will usually see them, the blade, it has like a continuous change in curvature, because let's say the blade is like this, but it is not straight like this, so it has like this curvature, and then it will make the manufacturing process much more complex. For this one, you just print from bottom to the top, so it's much more faster also. Moving on to the next one. Okay, we have again.
They use a lot of shape.
Yes, exactly. And it's more complex. Calculation, the computer can do. For the gearbox, basically the gearbox is, as I said, has a 16:1 reduction ratio because it's 2 stages. Each stage is 4:1, so each stage is 16:1. It will turn the turbine's lower speed and convert it to a higher torque. Because if it's a direct connection, then we won't provide sufficient torque for the generator. Okay? And then moving on to the piezoelectric. We have the piezo to be stacked on top of these court coasters. Why? Because basically piezoelectric works it will convert vibrational energy. Vibrational energy is when someone presses down, you exert pressure, and then it will result in a shearing force.
This one.
Yes, this is a flexible material. And then also, we cannot show it, but below here is a bottle cap. These two material are flexible material. So it will not only exert compressive pressure, but it will also exert shear force. You know shear force? Shear force is basically like the sideways force. Yeah, sideways force. So the sideways force, that's the vibration, and that's what we need to generate electric signals from the piezoelectric.
Not the pizza.
Yeah, the piezo itself is actually converts. It can be both either way, mechanical to electrical or electrical to mechanical. But in this stage, we convert mechanical to electrical. Mechanical in the form of shearing force, the vibrational energy. And then that's like. And then moving on to